Good day, everyone. So today we shall be looking at questions and answers on wave-particle paradox. Okay? Without wasting much time, let's dive into this. So we have example 1. It says, calculate the wavelength of an electron of mass 9.1 times 10 raised to the power minus 31 kilogram, moving with a velocity of 2.0 times 10 raised to the power 6 meter per second. Given that Planck constant equals 6.63 times 10 raised to the power minus 34 joule-second. Okay, so we solve this problem by writing out the parameters first. First of all, we have to calculate the wavelength. So the wavelength is unknown, is represented with this symbol lambda. So lambda is unknown question mark of an electron with mass. So the mass of the electron is given to be this value. So mass is 9.1 times 10 raised to the power minus 31 kilogram. And then the velocity of the electron is given to be 2.0 times 10 to the power 6 meter per second, that's V. And then the Planck constant is given, that is our H, to be 6.63 times 10 raised to the power minus 34 joule-second. Alright, so to calculate our wavelength is equal to Planck constant over the product of mass and velocity of the electron. Planck constant is 6.63 times 10 to the power minus 34, so it's written there. And then the mass of the electron is given also. So we substitute the mass, which is 9.1 times 10 to the power minus 31, multiplied by the velocity of the electron, which is 2.0 times 10 to the power 6. This is it here. So when we simplify this, we have the wavelength to be 3.64 times 10 to the power minus 9 meters. Simple, right? Yeah. So we go into another example, example 2. So here it says, if electrons are accelerated from rest through a potential difference of 10 kilovolts, what is the wavelength of the associated electrons? Accelerated electrons rather. So given that the mass of the electron is 9.1 times 10 to the power minus 31 kilogram, and the charge of the electron is 1.6 times 10 raised to the power minus 19 coulomb, and Planck constant is 6.6 times 10 raised to the power minus 34 joule-second. Alright, so in the course of solving this, we need to write our parameters. So let's start from the first sentence. The accelerated electron, move through a potential difference of 10. So we are given potential difference to be 10 kilovolt. So that means potential difference, which is V, is equal to 10 kilovolt. And we have to calculate the wavelength. What's the wavelength, right? So wavelength is this lambda, is unknown. Given that we have the mass of the electron to be this value, so mass of the electron is 9.1 times 10 to the power 31 kilogram, and the charge of the electron E is 1.6 times 10 to the power 19 coulomb, and also the Planck constant H is 6.3 times 10 to the power 34 joule-second. So to determine the wavelength, we use this formula. The wavelength, that is lambda, equals to Planck constant all over the square root of 2 EVME. Okay, why the E there is the charge, the V is the potential difference, and the ME is the mass of the electron. So we have these parameters already. H is given already to be there, so we bring it in. 6.63 times 10 to the power 34, all divided by the square root of 2 times the charge, which is 1.6 times 10 to the power 19, multiplied by the voltage, that is potential difference now, which is 10 kilovolt. So 10 kilovolt means 10 times 10,000, 1,000. So we have 10 times 1,000. Then multiplied by the mass of the electron, which is 9.1 times 10 to the power 31 kilogram. So when we put it here, everything simplified, we have our result to be 1.22 times 10 to the power minus 11 meters. Alright? Good. So we go to another example, example 3 this time. Here it says that the mass and wavelength of a moving electron are 9.1 times 10 to the power minus 31 kilogram and 1.0 times 10 to the power minus 10 meters respectively. Calculate the kinetic energy of the electron, given that Planck constant is equal to 6.63 times 10 raised to the power minus 34 jouleseconds. So to solve this, we write our parameters again. Yes, we are given the mass and the wavelength. So the mass is this value. So Ma is 9.1 times 10 raised to the power minus 31 kilogram. And the wavelength, which are lambda, is given to be 1.0. It's written out here. Then we have to calculate the kinetic energy. That the Ke is unknown, given that Planck constant is this. So kinetic energy by formula in this case is square of Planck constant over 2 times mass of the electron times square of the wavelength. Okay, so the Planck constant is 6.63 times 10 raised to the power 34 all squared is then multiplied by 2 divided by 2 times the mass of the electron, which is 9.1 times 10 to the power 31, multiplied by the square of the wavelength, that's 1.0 times 10 raised to the power minus 10 all squared. And when we simplify all of these using our calculator or using the law of indices, we have the kinetic energy to be 2.42 times 10 raised to the power minus 17 joule. Okay, so let's take another example. Here it says, calculate the minimum wavelength of X-rays when a voltage of 60 kilovolt is applied to an X-ray tube, given that the charge is 1.6 times 10 raised to the power minus 19 coulomb, Planck constant H is 6.6 times 10 to the power minus 34 jouleseconds, and then the speed of light, which is c, is 3.0 times 10 to the power minus 8 meter per second. So we go to solve this by writing out our parameters. So we have to calculate the minimum wavelength. So the wavelength is the question mark here, that's the lambda symbol. We are calculating this, given the voltage or potential difference to be 60. So V is 60 kilovolt, and the rest, the charge, is given the Planck constant and also the speed of light. So the wavelength is calculated in this way, that the product of Planck constant and speed of light divided by 2 times charge times voltage. So Planck constant is 6.63 times 10 to the power minus 34 multiplied by the speed of light, which is 3.0 times 10 to the power 8, all divided by 2 times the charge, which is 1.6 times 10 to the power minus 19, multiplied by the voltage, which is 60 kilovolts. So the 60 kilovolt means 60 times 1000. The kilo there means 1000. And when we simplify all of these, we have our wavelength to be 1.03 times 10 raised to the power minus 11 meters. Alright, so these questions are very simple, right? So we solved the last example for today, and that's example 5. Here it says, if the uncertainty in the measurement of the position of a particle is 5 times 10 to the power minus 10 meters, the uncertainty in the momentum of the particle is what? Okay, now given that the Planck constant is 6.6 times 10 to the power minus 34 jouleseconds. Okay, so we are told that the uncertainty rather of the position is given, that delta x is given to be this value. So delta x, which is representing uncertainty of the position, is 5 times 10 to the power minus 10 meters, and we are to determine the uncertainty in the momentum, that is delta p. Delta p is unknown, that represents the uncertainty in the momentum, given that the Planck constant is 6.6 times 10 to the power minus 34 jouleseconds. All right. So if you want to determine the uncertainty of the momentum by formula, uncertainty of the momentum is greater than or equal to Planck constant all over uncertainty of the position. Okay. So, and if we're going to substitute the value of h, that is 6.63 times 10 to the power minus 34 all over the uncertainty of the position, which is 5 times 10 to the power minus 10. When we simplify this, the uncertainty of the momentum will be greater than or equal to 1.32 times 10 to the power minus 24 Newton second. All right, so thank you for listening. See you another day. Bye.